Hello everybody, so today we're going to be finishing section 3.3. Today we're going to be able to define variation and standard deviation, and you're going to be able to compute these. Let's start with an example. Let's look at the results of a recent 6-person exam. Here we're going to look at the random variable x, which is the score. Say the first time we run the experiment, we have these results. So 2 people got 45, 1 got 90, and 3 got 100. And let's use this to put together a PDF. Well, if 2 got 45, that means 2 out of the 6 got 45. So there's a 2/6 or 1/3 chance that any given student was one of the people who got 45. Only one of them got a 90, so there was a 1 in 6 chance of somebody getting a 90, and a 1 in 2 chance, since there are 3 out of the 6 people who got 100, there's a 1 in 2 chance that any given student got a 100. And so, to compute the expected value, or the mean, we first multiply 45 times 1/3 is 15, 90 times 1/6 is 15, and 100 times 1/2 is 50. And putting all that together, we get the expected value of 80. Now let's say the second time we ran this, there was 4 people who got a 73, 1 who got a 90, and 1 who got a 98. Again, we can compute the probability distribution function, and we'll get that since there were 4 out of the 6 people who got a 73, we have a 4/6 or 2/3 chance of any given student having got a 73, and a 1 in 6 chance for 90, and a 1 in 6 chance for 98. Then 73 times 2/3 is 146 over 3. 90 times 1/6 is 15. 98 times 1/6 is 49 over 3. And adding those together, we're going to get 80. But notice that these two have the same mean. But notice also that if you were the person who got 90 in the first time, then you were in the bottom half of the class. Whereas if you're a person who got the 90 in the second time, then you're the second highest in the class. So, in other words, just because you know that the mean was 80, it doesn't really tell you how you did relative to your peers. It doesn't tell you where you lie relative to your peers. So, to compensate for that, we introduce something called the variance, and equivalently the standard deviation. Variance is defined by this interesting looking formula. To make it easier to read this formula, we often write mu, this is the Greek letter mu, for the expected value of x, for the mean of x. And then this formula has a nicer looking expression, and that's like this. So notice that we have both this guy here and this guy here. And I'm hoping that my mouse actually shows up on the screen, and we'll find out later. So, in particular, notice that you need to compute the expected value mu ahead of time. Okay. Intuitively, variance measures how closely packed the values of x are around the mean mu. Now notice that in these expressions, I have a bunch of squares. Why? Why couldn't I just use the expected value of x minus mu? Well, if you remember, the expected value of x minus mu, that's the same as the expected value of x minus mu. But by definition, the expected value of x is mu. And so mu minus mu is 0. And this is not very helpful. And so basically we introduce the squared here to get something that's non-zero. Okay, I mentioned earlier that we also had something called the standard deviation. Now, intuitively, the variance represents, and I'll fill in this blank space in a moment, intuitively, the variance represents the average distance of the value of x from mu. Now, if x has units, say it's measured in centimeters, then x minus mu also has units of centimeters, and so does x minus mu squared. And then x minus mu squared has units of centimeters squared. And so the variance of x also has units of centimeters squared. But if x is measured in mu, and we want to measure how is measured in centimeters, so we want to understand how far you are from the average value, you want that distance to also be in centimeters. But we have this thing in centimeters squared. We don't like that. So we introduce the standard deviation, which is just the square root of the variance. And when we take this into account, we should then think of intuitively variance as actually being the square of the average distance of a value of x from mu. Okay, let's do an example. Find the variance and standard deviation of this given random variable with the given probability distribution function. As usual, we want to start by computing the expected value of x. And as usual, we just take 0 times 1/2 plus 1 times 1/3 plus 2 times 1/6. And when we put that together, we're going to get 2/3, which is the expected value, which remember we're calling mu. Now there are two methods to continue, one using the first formula for variance and the other one using the second formula. They're both equally correct. So I'm going to start by doing what happens with the first formula. With the first method, we're going to find x minus mu for each value little x of big X. So we can extend our table. And in the first row, we're going to do 0 minus 2/3 to give us minus 2/3. The second row is going to be 1 minus 2/3 because it's 1 minus the mean 2/3, which is 1/3, and 2 minus 2/3, which is 4/3. And our step 3 is going to be to find the square of that new column that we just did. For this, we have minus 2/3 squared is 4/9. Remember that the square of a negative is a positive. 1/3 squared is 1/9. And 4/3 squared is 16/9. And finally, we need to compute the variance and the standard deviation from what we have. Well, the variance is just going to be the expected value of this random variable that comes from the last column here, using the probabilities we got here. Putting that together, we have 4/9 times 1/2 plus 1/9 times 1/3 plus 16/9 times 1/6, which when we simplify it, we get 5/9. And therefore, the standard deviation is the square root of 5/9, which is the square root of 5/3. Now, note that this form right here, and this form, are all acceptable. So any of these forms of the variance is fine. but you do need to know how to get between things. And same with the standard deviation. Now, I said that there was a second method, and that's using the other formula. In this one, we're going to start by finding x squared for each value little x of big X. When we do that, well, here we're going to get 0 squared is 0, 1 squared is 1, and 2 squared is 4. And then now we take the expected value of this new column, the x squared column, using the probabilities in this second column here, and we get 1/2 times 0 plus 1/3 times 1 plus 1/6 times 4, which all adds up to 1. And finally, we compute the variance and the standard deviation using our formula. The variance is going to be the expected value of x squared, which we just computed in step 3, minus mu squared. So that's 1 minus 4/9, which is equal to 5/9. And that's the same answer as we got before, as we expected, and therefore the standard deviation is the same as we got before. It's up to you which method of these two you want to use. I usually like using the second method. Some useful formulas. If y is ax plus b, then the variance of y is a squared times the variance of x. So notice that b didn't come into this formula. If you want to compute the standard deviation, then you just take the square root of both sides, and remember that the square root of something squared is the absolute value of that something. So the standard deviation of y is the absolute value of a times the standard deviation of x. Also, we can see what happens for binomial random variables, and one would get these formulas here, that the variance of a binomial random variable is n times p times 1 minus p, and the square root of that is the standard deviation. All right, I will see you guys at a future date, possibly, maybe virtually, and check out OWL, where I will have, below this probably, a bunch of questions that I want you to go and try and answer, and I will have my solutions below each question. Have a wonderful time self-isolating and social distancing and all that fun things. Bye-bye.